new new theme in our textbook and in our notes, and these are it kind of extends upon rate laws, and it involves this idea of decay. So remember what decay is. We measure a rate law based on the decay of the reactants. So for this reaction, A goes to B. Pretend you have a reaction A goes to B. Okay, so this A can decay. Okay, this A can decay. So the rate law is going to be K times the initial concentration starting material of reactant A, and that's raised to its order of decay. Okay, this A, lowercase a, the exponent, is the order of decay. So this order of decay can be zero order. Okay. It can be first order, or it can be second order. Okay, remember, A is the order of decay with respect to reactant A. With respect to reactant A. So let's say A decays with zero order kinetics. Okay, remember our profile here. Okay, the concentration over time of A goes down. It's the concentration on the y-axis. Meanwhile, our concentration of the products goes up. But to measure how fast, which we are calling the rate, we are measuring the decay of A. Okay, not the appearance of B, but the decay of A. And this is behind the entire idea of rate law. Okay, so just for this reaction, with respect to the reactant A, there's only one reactant, so there'll be one decay. So if A is equal to 0, let's plug in 0 here. These are the equations down here. So if anything to the power of 0 is 1. Okay, anything to the power of 0 is 1. So A to the power of reactant A to the power of 0 is 1. So actually rate is equal to K. Rate law is equal to K. The rate of change of A over time. So we're going to plot, rate of change, let me just put this here. Rate of change of A over time. So the minus sign, why is it minus? Okay, because it's a reactant, and the reactant is going to go down. So we plot concentration over time, and it's just a linear drop. Okay, anybody know the equation of a line? Okay, the equation of a line is y equals mx plus b. Okay, so m is the slope, b is the y-intercept. Okay. So this is if that reactant decays with 0 order. Rate is equal to k. One reactant, A goes to B. So remember, decay, the integrated rate law is going to be this. The concentration of A at some time t equals A naught minus KT. So you can, let me just say this, you can use this sheet on your exam. So bring this to the test so that you can use this equation. If it decays with 0 order, we'll tell you that. The problem will tell you that. So if it decays with 0 order, what equation will you use? this equation. Okay, so bring this sheet to the exam, rate law sheet. Okay, this is called the integrated rate law. It's from calculus. Okay, how many of you, just out of curiosity, have had calculus? One person? Okay, that's good. Okay, calculus. So this comes from calculus. So what is A naught? A naught is the initial concentration of A. Initial. Okay, that naught means initial. Okay, and this is A at some time t. Okay, what is K? What is K? K is the rate constant, what we've been talking about last week. And what is lowercase t? Okay, lowercase t is the time. Okay. Okay, lowercase t is the time. Right, so this is the equation you're going to use. And that is A decays with zero order kinetics. Okay, this is for the reaction A goes to B. So the concentration over time is a straight line. And like I said before, getting a line, for the people that are, like the calculus student who took calculus there, analyzing a line is really easy, okay? Because the slope is just minus the rate law. Okay, y equals mx plus b. All right, so let's say we have A and it decays with zero order kinetics. Okay, what happens if we double A? How fast does the reaction go? Okay, it stays the same. What happens if we triple the concentration of A? How fast will it go? Stays the same because the rate is just equal to K. Okay. Okay, that's if A decays with zero order. Right, and now we have another equation here, half-life. I think I saw a show of hands that some of you or most of you know what half-life is, right? Maybe generally speaking. So half-life is the time it takes for 50% of the material to be gone. Okay, remember this is all about decay. So the time, first of all, half-life is a time. Okay, time. So what is time to you guys? What is time? Seconds, minutes, hours, days, years. I think the half-life for plutonium, I don't know if it's zero, first, or second, but a lot of radioactive material, whether it's zero, first, or second order decay, will have half-lives in, centuries, like uranium or plutonium or something like that. So this half-life is a time. What is time? Seconds, minutes, years, decades, centuries, microseconds, milliseconds, okay, whatever it is. Some drugs in your body have half-lives of, milliseconds. That means after 10 milliseconds, 50% of the drug has been absorbed by the body. So it's a decay, okay, time in which the substance loses 50% of its concentration. It's a time in which the concentration decreases by 50%. So on exams, I ask a problem, calculate the half-life, and somebody puts 50 meters or something, or 100 degrees C. Okay? That's not a time, right? So what do we put in for your half-life? Okay, it's an actual time, so make sure it's whether it's seconds, minutes, years, whatever. It's the time in which 50% has gone or depreciated or has left. All right, so this is the equation for that half-life. Okay, so bring this to the exam, and this is the equation you will use if they ask you to calculate the half-life. Okay, for what order of decay? 0 order of decay. All right, and the units of K for this 0 order rate constant is m over s, molar over seconds. Okay, molar over seconds. Remember, capital M is molar. You will also see it like this, m times seconds to the minus 1. It's the same thing. Okay, it's the same thing. Now we will go to a first order decay. Okay, here's the equation. A goes to B. A is going to decay with first order kinetics. First order kinetics. So that means A is equal to 1. And if A equals to 1, what does that mean? Okay, let's substitute a 1 in here for the exponent. Anything to the power of 1 is what? Okay, so the power of 1. Right, so this is a first order decay with respect to the concentration of A. Okay, and it's going to be this rate. Okay. Again, the minus sign. Why is this A minus? Okay, it's a decay. Okay, but look at this graph. Okay, so for the math people, okay, this is very hard to decipher. Okay, the graph of concentration over time. This is a graph of the concentration over time. It actually kind of looks like what I told you at the very beginning. Okay, but how do we mathematically analyze it? Okay, if it's a first order decay, what we do is we do a linear transform. Okay, anybody know about transforms from maths? Okay, a linear transform is we try to convert it to a line. Okay, we'll try to convert it to a line, which is y equals mx plus b. Okay, how will we do that? Instead of plotting concentration over time, what will we plot? Okay, we'll plot natural log of concentration over time. Okay, this is called a transform, linear transform. So this is the equation you want to use. Okay, natural log of A equals natural log of A naught. What is A naught? It's the initial starting. Okay, how much you start off with, minus KT. Okay, which will be larger, A naught or A? A naught, because that's the initial. Okay, these are all decay, so A naught will be larger. After some time, it's going to decay. Okay, and that's going to be A at some time t. We can put time t here. Okay. So let's write down this equation. Natural log of A at some time t is equal to the natural log of A naught minus KT. This is if for this reaction A has first order decay. Okay, this is the equation you'll use. Like I said, bring this to the exam. Okay. Now, if you plot natural log of concentration over time, okay, you get that nice straight line, y equals mx plus b. That's what we want. Okay. The slope is equal to minus the rate constant. All right, let's go here. Okay, if A decays with first order kinetics with respect to reactant A, what happens if we double A? We double the rate. Okay. What happens if we triple A? Triple the rate. Okay. So this is in contrast with zero order decay with respect to A. This is first order decay with respect to A. And this is the equation for that. Half-life is 0.693 over K. Okay, natural log of 2 is also 0.693. Okay, it has to do with the integrating 1 over x. But okay, so natural log of 2 over K, or 0.693 divided by K. Okay, K is the rate constant. I had a student last semester who's like, she's like, what's this? Why are you telling me this? You know, I had a student like 0.693, and then you're putting natural log of 2. It's the same thing. Okay, natural log of 2 is 0.693, so they put 0.693. Right. So 0.693 over K. This is the half-life. What is half-life now? Right. Time in which how much is gone? The concentration is gone by how much? 50%. Okay, so this is the equation we use. Like I said, you can bring this to your exam. So no need to memorize it. And the units of K, remember the units vary, is going to be 1 over seconds. Now you can also write this as seconds to the minus 1. Okay, it's the same thing. All right, our last equations that I like to go over with you is if A decays with second order kinetics. A decays with second order kinetics. That means the A is 2, which means the rate is equal to okay, we're going to substitute the 2 here. Okay. K initial concentration squared. All right. So K rate constant, and that gets squared. All right, why the minus sign? Because it's a decay. Okay, we're measuring how fast based on decay. Okay, let's plot the concentration over time. What do you see? Okay, that same thing, which is hard to mathematically analyze. So this and this look the same. So how do you know if it's first order or second order? Okay, we will do that transform. In this case, instead of taking the natural log of the concentration over time, what will we do? Okay, to do our linear transform, we will take the 1 over. Okay, 1 over concentration over time. If you take 1 over concentration versus time and you plot it and you get a straight line, what is the order of decay then? Second order. Okay, second order. So this is the linear transform. Okay. So let me ask you this. How do you know when something is first order decay or second order decay? Okay, how do you know? Okay. Say it again. Yes. You have to take a natural log over time, and if you get a straight line, what do you know? It's first order. How do you know it's second order? Take over 1 of the concentration against time. If it looks like this, then you know it's second order with respect to that reactant. Okay, with respect to that reactant. Okay, good job. Thank you, Susanna. Otherwise, these two look the same. They look the same. All right, if it's second order decay, okay, we mentioned that the rate is equal to K times the concentration of A squared. This is just one reactant. What happens if we double A? Okay, what's 2 squared? Okay, we quadruple the rate. Okay, what happens if we triple A? 9 times as fast. Okay, what happens if we quadruple the starting amount of A? 16 times as fast. What happens if we 5 times the amount of A concentration? 25 times as fast the rate. Okay, so that's if it's second order decay. And here's that equation for its half-life. Again, I'm I'm not asking you to memorize these. I'm just asking you to know when to use the equation for plug and play. You know, plug and play. Okay, so for second order decay, it's 1 over A at some time t equals 1 over A naught plus KT. Okay, this is if you know that reactant. This is just one reactant. You got to do this for each reactant, but this is one reactant. Okay, and that reactant is going to have second order decay. And these are the half-lives, time in which 50% is gone, time in which 50% is gone, time in which 50% is gone. Use those equations. Right. Units for rate constant K, it's going to be m to the minus 1 seconds to the minus 1. You can also write it like this. Okay. You can also write it as 1 over m, 1 over... Okay, that's the same thing. This and this are the same. Alright, so like I said, bring to exam. I'll write that down here. Bring to the exam. I should have a copy, but if you have your notes, you can use those notes that you put in here. So bring to test 2. Alright, this will be, because you don't need to memorize, all these equations. All right, let's do some practice problems. All right, so let's go to page 10. We'll do a series of practice problems, and then we'll move on to the next part of this. How many pages do we have? 14. 17, 18 pages. All right, the reaction 2A goes to B is first order with respect to A. Okay, so let's highlight that. First order with respect to A with a rate constant of 2.8 times 10 inverse seconds. 2.8 times 10 inverse seconds at 80 degrees. Okay, so temperature, rate constant. Change the temperature, change the rate constant. Okay, I'm going to call that 2.8 times 10. I'm just going to call it 28 inverse seconds. Okay, which is the same thing, once again, to 28 over seconds. Right, how long in seconds will it take for A to decrease? Okay, remember, everything is about decay. Okay, how fast means how fast it decays, the reactant, from 0.88 to 0.14. Okay, so this is our problem here. All right, so first order, what's the equation for first order? Can someone tell me? Have it, Susanna? Okay, yes, I remember now. Natural log of A at some time t equals natural log initial A naught minus or plus KT? Minus or plus?
Minus.
Minus KT. Very good, thank you. So this is what we need to plug and play. Okay, first order. So what is A naught? 0.88 molar, so I'm not going to put units inside the natural log. I noticed in the exam people putting units inside the natural log. I don't think the math people like that. Okay, so no units inside the natural log. What is time t? 0.14. Okay, minus k. What's k? Okay, 28 over seconds. and this is time t. Okay, so it's just plug and play, literally. Okay. From plug and play, we will solve for lowercase t. What is lowercase t? Is it time or temperature? This is another thing, students. Okay, rates mean time. Okay, usually capital T is temperature, capital T. What is lowercase t? Time. Okay, decay, half-life, these are all times. All right, so we will solve for t here. So I'm going to do natural log of 0.14 minus natural log of 0.88 divided by minus 28 over seconds. Okay, this is going to equal to t, which is what I want. All right, so this seconds that's in the denominator goes to the numerator. Okay, it goes to the numerator, so that means seconds. And what's natural log of 14 minus natural log of 0.88? Okay, this will be our answer. So you know how to do this on our calculator. You should know, Sam, you took calculus, so this should be easy for you. Okay? No? Your face seems like it's like natural log of 0.14 minus natural log of 0.88. Did you guys, that's not right. Oh, and then the minus and minus cancel, yeah. So minus 1.8 seconds. Let's see here. Let's do 1.8 seconds. And then minus 1.8 times this minus makes it positive. So it's 1.8 seconds. Okay, this is what I'm getting. The minus and this minus cancel out to give you positive. Yeah, usually time is positive. Okay. All right, so initially A was at 0.88 molar. Okay, initially, and then after 1.8 seconds, how much is the concentration? After 1.8 seconds, how much is the concentration of A? 0.14. Okay, and this is the idea behind decay. Okay, it's decaying, but after 1.8 seconds, it's gone from 0.88 to 0.14. All right, so on the exam, you just plug it and play it. Okay, plug it in and chug it out. All right, let's move on to another problem here. Let's move on to page 11. All right, so I'll let you guys look at this on your own. Okay, so first order reactions and half-life. Some things about first order I got from your textbook, the old textbook. Now you have the ebook. Let's go ahead and jump into this problem here. We calculate the half-life of N2O5. Its decomposition and has a first order rate constant of 55.4 times 10 to the minus 4. Okay, so another first order one here. Okay, first order. So what's the equation for half-life at first order? Okay, go ahead and read me that equation. You have it there, Susanna. What's the equation for the half-life?
Equals natural log of initial A minus KT.
The equation for the half-life for first order is 0.693 divided by K. Okay, half-life. 0.639 divided by K. That's what the equation you'll use. Also, 0.693 divided by K is also the same thing as a natural log of 2. So the question is asking for half-life. Okay, so which is a time in which 50% of the material is decayed or gone or reacted. Okay, so 0.693. K, what's K? 5.4 times 10 to the minus 4 inverse seconds. Inverse seconds, seconds to the minus 1. And this inverse seconds, if I move it up to the numerator, it becomes seconds. What is this on our calculator? Uh, 1283 seconds. Okay, this is what I'm getting. 1283 seconds. It's a time. 1283 seconds. What is 1283 seconds? 1 minute is 60 seconds. 21.4 minutes. After 21 minutes, this thing is gone. 50% of it is gone. Okay? Reacted, dissipated, evaporated, whatever it may be. Okay? Which is the same thing as 1283 seconds. Okay, let's remember half-life. Okay? It's a time in which 50% of the material is reacted or gone. For first order, zero order, second order, they have different equations. Okay, this is a time. All right, so first order, half-life first order. Let's see, I think there's a second order problem on page 12. And let's go ahead and do that, okay? Okay, this is a second order problem, all right? All right, the reaction 2A goes to B is second order. Let's highlight second order here. Second order with a rate constant of 58, inverse molar, inverse minutes at 24 degrees C. All right. Starting with an initial concentration of 0.0092. How long, this is a time, how long will it take for AT to equal 3.7 times 10 to the minus 3? And in part B, they ask us to calculate the half-life. So the half-life is pretty easy. We can use the equation. The decay, how long it will take for it to decay from this concentration to that concentration, is also easy. We'll use our equation. What's the equation for second order? It's second order, right? Yes. Okay, so look at our rate loss sheet, and what is the equation for second order? Second order, what's the equation? Go ahead. what equation will we use here? Okay, part B is calculating the half-life, but what's part A? What equation can we use? What's the equation? Just read it, Susanna.
I did. Is it the 1 over...
There you go. You got it. 1 over A. Good job. 1 over...
Plus
Yes,
K.
correct. Okay, this is the equation we'll use to calculate part A. Okay, very good. Thank you. Okay, awesome. Awesome job. All right, so again, you don't have to memorize that. You just need to know what equation to pluck out. All right, what is A naught? Okay, it's point. Yeah, but what is it in this problem? 0.0092. Very good. What is A at some time t? 3.7 times 10 to the minus 3. 3.7 times 10 to the minus 3. I'll just do 0.0037. All right, plus K. What is K? Okay, this is our K. 51. I'm going to move the M down and the minutes down. Okay, you don't have to, but I'll just go ahead and do that. Okay, M to the minus 1 is M in the denominator. Minutes to the minus 1, it's minutes to the denominator. And we are solving for T, right? So just plug and play. All right, so how will we solve this? Okay, we'll do 1 over 0.0037. 1 over 0.0092 big M, okay, is going to equal to 51. Okay, times T. Okay, so we will solve for T. Everyone okay with this algebra? Okay, good. Okay, we're just plugging and chugging. Plug and chug. All right, I moved this 1 over 0.0092 to the other side of the equation. And what is this on our calculator? Okay, minus divided by 1 divided by 0.0092. I'm getting 161.575. Okay, I will add some extra digits in there. 161.575 divided by M, okay, equals 51 inverse mole inverse minutes times T. Okay, now we'll solve for T. This should be able to solve our problem. Okay, once Susanna gave us the right equation, all I had to do was plug in and chug, get the answer out. All right, we will solve by cross multiplication. Okay, we'll cross multiply out. So that is 161.575 big M times minute. This goes here, this goes there. This goes to 51M. That is equal to T. Almost forgot this for a second here. Okay, this and that. Yeah. Okay. Okay, or divide by 51. All right, the big M molar cancels. We are left with minutes. What is 161.575 divided by 51? Oh. 3.1, let's see how many. Let's do 3.2. Let's do 3.2 minutes, okay? Or if you put 3.17, that's fine also. 3.2 minutes. So the time here is going to be okay, this is the answer. So after 3.2 minutes, okay, this is going to go down from 0.0092 to 0.0037. All right, part B. Okay, so we'll have a couple of these on the exam, so it's good to practice these. Let's do part B, which is the half-life. Okay, so what's the equation for the half-life? So I know you have the sheet, so I'll ask you, what's the half-life equation, Susanna? Yes. Okay. So why did she choose this one? Because it's second order. Okay. Why did our classmate choose this equation to plug it in? Because it tells us, the problem tells us it's second order. So all we got to do is plug in our values. What is K? Excuse me. Oh no, something's happening in my throat. 51 inverse M inverse seconds. Okay, I'm going to move the M to the up. I think I can do that. M minus 1 is actually M to the power of 1 in the numerator. Minutes is to the minus 1 is minutes to the numerator. 51. That's K with the units. What's A naught? 0.0092. Okay, big M. Okay, the M's get canceled. And then what's 1 over 51 times 0.0092? 2.13 minutes. Okay. Good job. Okay. 2.13 minutes. So that's the answer. All right, let me ask you this. I'll ask you this question, Sam. Okay. Initially, you are at 0.0092 of this substance. Okay, how much will this substance be at? What will be its concentration after 2.13 minutes? At time 2.13 minutes, what will be its concentration? It's a half-life. Half-life. So what will it be? That's half-life. So what is the half-life definition? It's a decay, but a decay when how much of it decays? 50%. So you're going to divide it by 2. Very good. That's about 0.0046. Okay, so that's the definition of a half-life. Okay? 50% of it is gone at 2.13 minutes. Why 2.13 minutes? Because that's the half-life that we calculated. All right, so at 2.13 minutes, this will go from 0.0092 to 0.0046. Okay, half. Okay, not double, half. So we half it.
You don't need to know the half-life if you want to know the concentration, right? Because you just divide it by 2 if you already have A naught. Is that what I'm understanding? If you were just to ask the concentration after half-life, then you would just divide A naught by 2.
If you know the half-life, yes. If you know the half-life. If you know the half-life, if they give you the half-life, you just divide it by 2. But how do you calculate the half-life? Okay, If it's second order decay, you'll use that equation. If it's first order decay, you'll use 0.693 divided by K. And if it's zero order, you'll use that equation, okay, whatever it's in our sheet. Yes, once you calculate the half-life, you divide by 2. That's correct. Very good. All right, I'll end class now. I have something happening in my throat, so we have 5 more minutes, but we will finish this up Wednesday. I want to finish this chapter up by this week and move on to chapter 14 next week. All right, so that's my plan. Let's aim for that so that we can, once we finish it, not so fast, but also not so slow, we'll have more time for review and such.